So, good morning, everyone. I think we can start. Welcome to the first BIOPOLY Cluster webinar to celebrate the launch of it, titled Accelerating Innovation in Bio-Based Polymers. So thank you for joining us today. My name is Arantxa Iborra, and I will be moderating this session on behalf of the BIOPOLY Cluster team. Before we begin, let me walk you through today's agenda. We will start with a short video message from Simone Macaferri from the CB Joint Undertaking, who will share a few welcoming words and highlight the importance of synergies across projects in order to leverage on complementarities in view to further scale up and policy feedings. Simone was originally scheduled to join us today live, but due to a last-minute unexpected event, he is unfortunately unable to join. However, he has kindly recorded a short video message for us to open the event and share his contribution. After that, we'll move on to the presentations from three projects that make up the cluster, the BIOPOLY cluster. So these are POLYMEER, BIOPYRANIA and POLYMERS-5B, each introducing their approach to developing innovative, sustainable bio-based polymers. And then we'll continue with a panel discussion titled Bio-based Polymers in a Circular Future, where our speakers will explore key topics such as feedstock availability, industry demand and application sectors, policy and regulatory frameworks, and opportunities for collaboration. Finally, we will close with a Q&A session, so please feel free to post your questions at any time in the chat. So now let me briefly introduce what the BIOPOLY cluster is and why it was created. This cluster was established some months ago by the three projects that you can see, POLYMEER, BIOPYRANIA, and POLYMERS-5B, all funded by the CBE Joint Undertaking. The idea behind the cluster is to foster collaboration, exchange best practices, and amplify the impact among projects working on similar themes. Each project focuses on different types of bio-based polymers and feedstocks, from brewers' spent grain to agri-food residues and woody biomass, but they all share the same vision, which is to advance sustainable, circular, and high-performance materials that reduce Europe's dependence on fossil-based plastics. Through this collaboration, we aim to accelerate innovation, strengthen communication, and help shape the future of the European bioeconomy. So now let's begin our session with the video message from Simone Macaferri, representing the SCB Joint Undertaking. Please let me know in case you cannot hear it. So we can thank Simone and the CB undertaking for their support and for setting the scene today. Now we can hear directly from the project. So I'm pleased to introduce our first speaker, Assunta Marroquí, coordinator of the Polymer project from the University of Perugia. The floor is yours, Assunta.
Thank you, Arantxa. I will share my screen in a while. Okay, can you see it?
Yes.
Good. So, good morning, everyone, and thank you for joining us today. I am pleased to introduce POLYMEER. POLYMEER is a project that started in September 2024 and will run for 4 years, focusing on the development of bio-based and circular polymer solutions. And to go into the aim, Polymer aims to create a sustainable value chain that starts from brewer spent grain. Brewer spent grain is the main byproduct of the brewing industry and delivers eco-designed bioplastics for real industrial applications. We focus on 3 application areas, that is agricultural films, tertiary packaging, and automotive textiles. Polymer brings together 14 partners across 8 countries, including universities, research centers, small, medium enterprises, and large industry players. This allows us to cover, let's say, the entire value chain from raw material supply to polymer design, processing, scale-up, application testing, and sustainability and market assessment. So here the context, let's say that today bioplastics represents less than 1% of global plastic production. So the potential for sustainable alternatives is very large. But many current solutions still, I have to say, fall short because they may be bio-based, but not recyclable, not biodegradable, or they don't achieve the performance which is required for real applications. And this is where Polymer steps in. We are developing high-performance bioplastics from brewer spent grain, aiming to reduce the environmental impact, lower reliance on fossil fuels, and create viable circular markets. To do this, what we can do, we start by fractionating brewer spent grain, like here, and recovering protein first, and then lignin, cellulose, and hemicellulose. These fractions are then converted into new monomers and polymers through green and waste minimized processes. This development is progressing from lab scale to pilot here to ensure that the process is robust and ready for industry. And importantly, the end of life is designed from the start. Recyclability and biodegradability are part of the polymer design, and this is supported by LCA, techno-economical, and social acceptance studies. All this feeds into our 3 application areas that I will introduce next. So the first, agriculture. In agriculture, we had to say that traditional plastic mulch films like LDPE are a major contributor to soil pollution because they are fossil-based and not biodegradable. Even the biodegradable films, which are already on the markets, don't perform well often in the field due to weathering and durability limitations. And this is where Polymer steps in. We aim to developing BSG-derived copolyesters to produce soil biodegradable mulch films that can match or even exceed the performance of current biopolymer solutions. We bring two distinctive advantages, which is first, that the polymer is designed to realize phosphate during degradation, meaning that the film can act as fertilizer, returning value directly to the soil. And second, we incorporate biochar derived from BSG itself, which provides UV stability for field durability, and after biodegradation, it remains as a soil improver. Then we have the automotive sector. In this case, polyesters dominates car seat fabrics because of its durability, UV resistance. But it is fossil-based and extremely difficult to recycle, especially once it is laminated or combined with other components. So Polymer is developing new lactone-based polyesters from BSG that are designed to meet these same performance requirements, and at the same time introducing a clear environmental benefit. The key innovation here, as you can see, is let's say the integration of phosphate units again into the polymer backbone. And by tuning how these phosphate units are incorporated, we can achieve slow controlled biodegradation over several years, and this is suitable for the lifetime of the products. And importantly, those phosphate units act as intrinsic flame retardants, meaning that we don't need additional flame retardant additives, and this simplifies the material formulation and for sure improve recyclability. Then we have tertiary packaging, and in tertiary packaging, especially pallet wraps, materials like PVC, polyethylene are widely used because they are reliable. So at the same time, they are fossil-based, not biodegradable, and often require clean additives, and this increases environmental impact and cost. Polymer takes a different approach, which is to develop vitrimeric materials from BSG, enabling, for example, breweries but also other industrial sectors to use their own, but specifically breweries, because they can use their own byproduct to package their own goods, and this creates like a local circular loop. Vitrimers are attractive because they combine mechanical strength with recyclability thanks to the dynamic covalent bonds that enable reshaping and reprocessing. We are also exploring bio-based additives, sprayable Vitrimer coatings, and this can simplify processing and industrial adoption. What I want also to add is that polymer is not only about developing new materials, because it directly supports Europe's sustainability goals by upcycling U.S.-spent grain into recyclable and biodegradable bioplastics. We contribute, for example, to the Circular Economy Action Plan and the Zero Pollution Ambition. Our soil biodegradable agricultural films align with farm to fork and soil health initiatives, for example, and we ensure compliance with REACH regulations so the materials are safe and suitable for industrial uptake. And next, polymer also brings tangible benefits for people and the environment. It will help reducing reliance on fossil plastics, for example, and supports real circularity across the entire value chain. It contributes to greater public awareness and acceptance of bio-based solution, and it also will bring economic benefits, helping companies diversifying their product portfolio, for example, and remaining competitive as markets move towards sustainable material. At the local level, we can help creating value where the resources is produced, for example, strengthening regional supply chains and supporting new job opportunities in the bioeconomy. Well, I just said the project officially started in September 2024, but we already have very promising results. I want to show you just one example. We have reached one of our early milestone or schedule. And this milestone is about the optimization of a safe and sustainable by design and reliable fractionation process for brewspent grain. We indeed have developed two alternative protocols, a sequential fractionation process and a simplified two-step route. We are now working together with the BBPP partner to determine which one offers the best balance of performance, scalability, and operational efficiency for the pilot phase. What you see here is the sequential process with the extraction yields. It builds on patented knowledge developed at the University of Perugia, which we have now further developed and optimized. And two aspects are particularly important. We process the PSG in its wet state, exactly as it comes from the brewery, avoiding drying, reducing, for example, in this way, energy use and improving for sure sustainability. And next, this process also includes reactive extraction steps that enables us to selectively isolate hemicellulose into a functionalized form. And this provides added value for subsequent polymer synthesis. So this is the first, I can say, concrete and resource efficient results. I want to close this presentation by showing you this picture from the last consortium meeting we had at the Birra Peroni facilities, which is, as you might have understood, one of our partners. And thank you all for your attention.
Thank you so much, Asunta, for your presentation. I think you gave us a very nice overview about what Polymer is doing. So now I am pleased to welcome our next speaker, which is Professor Luis Joaquim Pina da Fonseca, coordinator of Polymers-5B from the IST-ID Institute for Bioengineering and Biosciences in Portugal. I give you the floor, Luis.
Thank you very much, Antje. So let's go to find my file. So everyone see well the slide?
Yes, perfectly.
Okay, so thank you very much for your organization and the participation in this cluster. So Polymers-5B is the focus in the synthesis of bio-based and biodegradable polymers and copolymers based on the extraction of monomers from renewable bio-wastes using biocatalysis and green chemistry to contribute to the European circular bioeconomy. So the Polymers-5B journey is can focus in the agri-food residues to sustainable plastics. So basically the feature of Polymers-5B project, so as I told in the title, So we developed an alternative bio-based polymer synthesized from bio-based renewable monomers. It's constituted by 13 partners, led by ESTD and my Institute of Research, Institute for Bioengineering Bioscience, where the proposal was written and built. So we use the food side stream and the wood processing residues as feedstock. And I'm going to tell something more in detail later. So we use biocatalysis and chemics based and with the help of safe and sustainable by design and combined with artificial intelligence and machine learning tools that help us with the control since the beginning the quality of the process and the environment issue that are going to rise. So the focus of these bio-based polymers is to deliver solutions for textiles, in particular swimming wear, automotive, so some plastic material inside of the cars, furniture, to putting some materials, and the polymeric resins market, in particular to immobilize enzymes and purify water. So the idea is to produce these polymers, but as we are going to use feedstocks from different agro and food industries, so there is a possibility to produce and release other bioactive compounds that we can eventually satisfy some market demands. And in this case, we are focusing build biorefineries in the to extract all of these compounds. So, as I told you, so basically we have 677 research centers. We have 4 CMEs and 2 large companies that are distributed in Portugal, Spain, Italy, Serbia, Germany, and Latvia, basically. So we are in this moment in the first preparing the first report as we starting in the July 1st, 2024. So it is a good opportunity to organize the results and to show you some of our progress in these 18 months. So basically the extraction of tomato pomace that we starting to work in the beginning. So we start by separating the skin from the seeds of the tomato and go directly to produce dicarboxylic acid and hydroxy acid that mimic the coating plastic of tomato, and then trying to produce bio-based monomers and polyesters with this direct strategy. This direct strategy showed that was impossible, because when we dry the bio-based monomer, you obtain a plastic thermoset plastic that is difficult or impossible to work so easily, at least at low temperatures, and we dry this in 65 degrees. So we have to starting to again, and then move for a very cascade integrated process that we starting to separate several compounds, as you can see in the diagram. And in the red, we have the mainly raw materials and some reactants. In black and the blue, we have intermediate compounds that we can extract in this moment. And in green are the bio-based monomers that we can extract and use them. for polyesters, mainly for polyester application, and some bio-based bioactive compounds that we can commercialize. Inclusive in this moment, we starting to have some media that is possible to use in the fermentation, substitute yeast extracts, peptones, and other compounds. And we are in this moment to use this also to produce cellulases and itaconic acid. So the same thing happened with the extraction of bio-based monomers from olive oil pomace. So in this case, we have a similar diagram. In this moment, we are trying to conjugate both process and use the same steps of the industrial units that we can eventually have a common part. And this common part is particularly interesting because we are focused in this moment in the extraction of polyphenol compounds in a similar route for tomato and olive oil processing, if possible. Basically, all of the compounds that we can achieve in the end are exactly similar. So bio-based monomers for polyesters and other products that we eventually can focus in the production of the materials and polymers and copolymers for the prototypes that are designed in our project. So again, we have other the raw materials, the intermediate compounds, and the green one, the possible materials for polyesters and polyurethane production from the olive oil processing pomace. So as you can see here, we show the progress that we achieve in this more or less 1 year. So we have a little problem in the beginning of the project because we lost the first campaign of tomato and olive processing in 2024. But now we are trying to recover this time and achieve, as you can see, the progress from very red color of the protein monomers to in the last picture, the almost white or very white bio-based monomers for this application. So this was a huge work and several steps that include inclusively, as you can see here in the middle, the extraction of carotenoids that are mainly responsible for the red color. So the extraction of polyphenol from tomato, but mainly from olive oil pomace. So we are using the water. So we suspend the olive oil pomace in water, so make some agitation and starting to extract the several compounds, in particular polyphenol, and then we can, in this moment, trying to use solid liquid chromatography or adsorption and insertion to purify this polyphenol, and the methodology is very common to the polyphenol from tomato and olive oil. So it is in this moment the steps of concentration and partial purification, but the goal is to include additional liquid extraction to purify completely some of this polyphenol. So as you can see here, we have a very high purity of carotenoids, so in particular lycopene. So we think that it's possible to use this for cosmetic, pharmaceutical, food applications. And here in the right, you can see the one profile of the extraction of polyphenol from olive oil polymerase in water. So as you can see, the biggest peak is hydroxytyrosol, and the right one is tyrosol. So we are trying to focus the extraction and purification in these two polyphenol, hydroxytyrosol and tyrosol, because we would like to use this in the mimic of the PET, so as a semi-aromatic polyesters, as I'm going to show you later. So one of the main focus in the first year of the project is to synthesize building blocks with functional groups. In particular, because we want to facilitate the biodegradability of these polymers, so we would like to incorporate these functional groups in the polymer chain that can eventually facilitate or the biodegradability is more easy. So we're starting by combining one of the polymers, subbaric acid and eternodiol, and we easily incorporate the glutamate, releasing the amino group in the main chain. So we are in this moment trying to see if it is possible the polymerization of this material and release the monomers. So subbaric acid, eternodiol, we have already 90% of hydrolysis and release of these monomers, and we in this moment trying to check what happened with the incorporation of glutamate in the polymer chain. So as I told you before, we are in this moment focused to the semi-aromatic polyesters. So the idea is to trying to substitute and mimic the properties of the PET. So we study several semi-aromatic, but the goal in this moment is focusing hydroxytyrosol and tyrosol. So for this reason, before we go to the bench, we have a huge number of experiments. We ask some of our partners, in particular Centifin, to help us with the simulation of the properties between the hydroxytyrosol and several aliphatic fatty acids, succinic acid, oxalic acid, sebacic acid, and itaconic acid. So the Centifin performed this modulation simulation of the properties that you can see the structure, and fortunately we starting to have very similar properties that can mimic the PET. So in this particular case, we have some more difficult to find the simulation of the mechanical properties in young models, and the yield stress. But in this moment, we are proving, or at least the simulation can open the opportunity to generate a new generation of semi-aromatic polyester based in the hydroxytyrosol. So as you can see, the green region is the properties of the PET and the simulation of the properties that I showed you before with the simulation data. So there is other groups of the polymers-5B, in particular from Latvia, that are starting materials from wood and lignin processing, side stream, in particular tall oil fatty acids. So in this moment, the group of Latvia is already performed several polymers that test in as you can see here in this slide, and in particular mechanical properties, because we would like to use this material to coating furniture or to use in other applications. So the recycle of this material is very important, and this group already starting to perform some experiments to reduce the size of these materials, eventually make solvolysis and the hydrolysis of the monomers and trying to recirculate. So this is something that we are trying to optimize and as soon as possible to contribute to circular plastic economy in Europe. Okay. The group from Serbia, the Faculty of Technology of Novi Sad, so it dedicated to study the synthesis of green polyester with the microwave-assisted process. So they select 3 acids and 2 free diols and 2 Crandall catalysts. In this case, this group are going to use the polymerization based in metallic catalysts, but the monomers are from renewable source. So in this case, exosorbide, ethylene glycol in 1,4-butanoediol using the tartaric acid, succinic acid, and malonic acid. So in this case, we get success with 60 successful samples of these diverse polyesters. So in this case, we are going to test them later to check the circularity of these polymers and the hydrolysis and release of the monomers for posterior synthesis of new polyesters or other plastic materials. I would like also to give some relevance to the group of Max Planck that from Germany that are contributing with us in the synthesis of polyamides. So the idea is to have a green synthesis, more efficient, and trying to contribute to zero carbon footprint. So the polymerization is using ionic liquids and also the possibility to reuse these materials with these ionic liquids to dissolve the polyamide, perform the 3D printing, powder, Schefferlit, mini-emulsion, latex, and so on, and then eventually reuse the ionic liquids to trying to minimize the contribution to environment. So this is some examples of the size of the polymers so that we obtain by this processing by the Max Planck, but there is so it is necessary to increase the molecular weight, reduce the size distribution of the particles, and ensure steady fiber production. So we are in the first 18 months of the project. We have already several kind of polymers, thermoset, thermoplastic polymers that we are going to use in the next period to trying to produce the prototypes for the plastic application that I name. So textile, automotive, furniture, and polymeric resins. So there are other groups contributing for the project, in particular the Aerocat with the studies of safety and sustainable by design. Since the beginning of the polymer, we are in this moment starting to collect some of the reactants conditions of the polymerization. We have also hidden air that help us with the optimization of the extraction and the synthesis of the polymer process. And the final group of partners that are going to test and validate these polymers for the industrial application that I name, and also the NESB, that is our partner that are helping us with this cluster, the Ricardo Varoto, that help us to participate in this cluster in the dissemination and exploitation of our results on the project. So I finish my talk. Thank you very much for your attention, and any question I answer later.
Thank you so much, Luis, for your detailed presentation. Now, I would like to welcome our last speaker, which is, one moment so that we can see her. So we have Katrien Bernaes as last speaker, coordinator of BIOPYRANIA project, and she comes from the Maastricht University. So the floor is yours, Katrien, whenever you want.
Thanks. You see my presentation?
Yes, but not full screen. Now, yes, full screen.
Okay. Yeah, I'm the coordinator of the BIOPYRANIA project on bio-based monomers from second generation biomass for high performance polymers, copolymers, and blends. And our project started the 1st of October 2024, lasts for 4 years, 4.9 million euro budget. And I am the coordinator at Maastricht University. So the consortium consists of 7 SMEs, 4 academic partners and RTOs, and 2 large industry partners spread over whole Europe. And in total, we have 13 partners and 9 countries participating. So the context of our project is that the Sustainable Product Initiative, the European Green Deal, they set a challenge for the European industries to create sustainable products where we consider environmental impact, durability, recyclability, and safety. And we use a new class of bio-based monomers that will be synthesized from amino acids that are obtained via fermentation from second generation woody biomass. And the main goal is to develop new classes of bio-based polyamides and polybenzimidazoles and their copolymers and blends in a safe and sustainable way from lab scale to pilot scale. And we look for applications in automotive and in green hydrogen sectors. So for the automotive, we want to use the polyamides in electrical vehicles. And for the green hydrogen sector, we want to use the polybenzimidazoles as membranes for fuel cells and electrolyzers. And we also look at recycling of the materials. Furthermore, we have also support in the project via digital methodologies, environmental, toxicological, techno-economic, and socioeconomic impact studies. So the specific objectives of the project are the development of safe and sustainable processes for the creation of bio-based building blocks, starting from second generation biomass, develop new bio-based polymers, polyamides and polybenzimidazoles using safe and sustainable processes, use those polymers to make polymeric materials and blends according to the requirements of the end users in automotive and energy sector, and do validation. And we also think about recycling, mechanical and hydrothermal recycling, and also to process design towards pilot scale production. So we have in our work package, in our project, 7 work packages. In the first is user requirements and test design. In the second, we go from biomass to raw materials, being amino acids and monomers. In the third, we synthesize bio-based polymers and copolymers from those monomers. In the fourth, we use the copolymers and the polymers for blending and for validation studies in membranes and polyamide compounds. And we look also at recycling. And we also do demonstrators in the automotive and energy sector. Work package 5 is on safety, sustainability, and techno-economic assessment. Work package 6, communication, dissemination, exploitation. And work package 7 is on project and innovation management. So here you see how the different partners in our project belong together in the value chain and how we interact. So we start from second generation woody biomass, and our partner Fibronol does the biorefinery to make sugars and lignin, and those are used to make amino acids via fermentative process, where the lab scale developments are done by University of Saarland, and the upscaling pilot scale is done by Biobase Europe pilot plant. Then we obtain amino acids, and BIOPLASTICS converts those amino acids to monomers. And those monomers are then used by Maastricht University to make polyamides and polybenzimidazoles at lab scale. And later, BIOPLASTICS will do the upscaling of the polymerization. The polymers are then exchanged with more application partners. So the polyamides with Arkema, who does polymer processing, blending, and compounding. And Stellantis will evaluate the materials in electrical vehicles. For the polybenzimidazole value chain, we will use the polybenzimidazoles to make anion exchange membranes, and Tecnalia is involved to make those membranes. And then the membranes are used by Hydrolyte to make the fuel cells and electrolyzers. The expected outcomes is the availability of a broader range of bio-based products meeting market requirements, unlocking new applications not covered by bio-based polymer, improved safety, sustainability, and circularity compared to fossil-based state-of-the-art benchmarks, evidence of promising product and process performance for reference applications in view of subsequent upscaling, significant improvements in environmental performance across the value chain against specific fossil or bio-based benchmarks, and improved circularity and resource efficiency via practical application of circular bioeconomy concepts. And then we come to the first result. So Fibronol, they use 2G biomass, 2G woody biomass to do biorefinery. And they delivered C5 and C6 sugars, C5 xylose rich, C6 glucose rich. And they did special developments for preconditioning and removal of inhibitory components for fermentation to make the sugar streams ready for fermentation studies. And University Saarland did lab scale studies on strain and bioprocess development to develop 2 amino acids. And currently they achieve with the first amino acid a titer of 5.1 gram per liter, and with the second 0.3 gram per liter. And they are now in the process of increasing the titer to make the process transferable to Biobase Europe pilot plant for piloting. And we target for the first amino acid a titer of 40 to 50 gram per liter, and for the second 10 to 20 gram per liter. And BIOPOLYMERS worked on the monomer synthesis, where we look for two monomers, one monomer from the first amino acid and a second monomer from the second amino acid. The first monomer, we are quite far already. We already made 500 gram, and we started from a lab scale process. And BIOPOLYMERS improved that process with respect to safety, energy, and yield, 10% increase in yield. And IRIS helped with the SSBD and the LCA studies. For monomer 2, we are currently at 100 gram scale, and we are working on improving the yield. Then the next step for BIOPOLYMERS is to upscale monomer 1 to 5 kilogram scale. At Maastricht University, we use those monomers to make polyamides and polybenzimidazoles. And for the polyamides, we made already homopolymers. We developed the process. We can, depending on the choice of the diamine, tune the melting point between 120 and 280 degrees. And our molecular weight is, depending on the choice of the comonomers, 20 to 65 kilogram per mole via GPC. For the polybenzimidazole, we are still having challenges to do the synthesis in a green way. And in order to avoid retardations in the further process, where people are expecting samples to do membrane fabrication, we provide initial samples prepared in solution. And the next steps are for the polyamides to study physical properties, make copolymers, upscale to 100 gram, so Arkema can do some compounding. And for the PBI, we are also now upscaling the solution synthesis to provide enough material to Tecnalia to make anion exchange membranes. And here you see a picture of our taken at our last consortium meeting in Tallinn at the Fibonal. And if you have any questions, please let me know.
Thank you so much, Katrien, and thank you all the speakers. I'm sure the audience is now a bit more aware of what we are doing in the 3 projects involved in the cluster. So now let's move into our panel discussion to explore together opportunities and challenges for the bio-based polymers in a circular future. We will cover some topics like we already mentioned for feedstock application policy and collaboration. So let's go to the first question on feedstock availability. It says, one of the challenges for bio-based polymers is ensuring sustainable and sufficient feedstock supply. How do your projects address this issue, especially when working with residues like brewers' spent grain, agri-food waste, or woody biomass? So we can maybe follow the first, the same order that we had for the presentations. So if you want, Assunta, go ahead.
Yes, thank you, Arantxa. Well, regarding polymer, our strategy, I have to say, relies on the fact that brewer spent grain is producing at massive scale. It's considered that it accounts for around 85% of all brewing residues. And globally, this means roughly 40 million tons per year, with about 8 million tons generated in Europe alone. And because beer is produced continuously throughout the year, BSG is not, it's like a non-seasonal, I have to say, and reliable, therefore, feedstock, which helps avoid the supply chain volatility, for example. And also, I want to add that in our project, we are not just using this residue, but we are applying like a cascading use approach. This means that we don't displace its current beneficial uses, such as, for example, animal feed, but we focus on the fractionation of PSG that would otherwise end up in landfills. And we separated it into biopolymers, which are cellulose, hemicellulose, lignin. We separate proteins also so that each component can be directed toward the application where it brings the highest added value indeed. So it is an approach that ensures efficient resource utilization and also minimizes waste and at the same time maintains the existing value chain.
Great. Thank you. Can you continue with your answer, Luis, if you want? You are muted.
Thank you, Arantxa. So in particular, the polymers 5B, so we have the wood, the lignin residues that are going to be explored by the partners from Latvia. So this is a huge amount available in the north of Europe. So I suppose there is enough availability of this kind of feedstock. In the case of tomato and olive oil, so these are feedstock that are producing in large amount in the Mediterranean region, so in particular Portugal, Spain, Italy, and the north of Africa. So we think that the collaboration that we have with Conesa Portugal, that they have a capacity of 1 million tons of tomato processed per year. In this case, in 2 months, it is a very huge, but the residue of that is between 5 and 10% of the residue that we can use in this processing of tomato for past source and other kind of the products that produced by this company. And if we have success with the optimization of the cascade integrated process of the tomato and olive oil, that the mainly goal in this case of olive oil is to minimize the negative environment impact of the polyphenol compounds that are resistant to microbial degradation. So in this case, we have also a huge amount of residues that is generated by the production of olive oil in Portugal. And the same thing happened in Spain and Italy. So in this case, with the success of the biorefinery that I would like to implement here in Portugal, we can transfer the know-how to the other countries, Spain, Italy, and eventually north of Africa, to be very near of this kind of bio-wastes produced by this feedstock industrial processing, and then to have enough bio-based monomers and bioactive compounds that can profit the biorefinery that are the kind of process and the industry that are going to generate with these studies in polymers 5B. All of these biomaterials can then transfer to the plastic production. So if you have success with the application in the textile, as I told you before, swimming wear, automotive, the interior of the cars, and furniture and polymeric resins, we can supply the European bioeconomy with the new materials that use feedstock originating in Europe. Of course, the idea is to compete and substitute some of the materials that are producing the plastic materials produced from fossil-based feedstock.
Thank you, Luis. So, Katien, do you see similar challenges or different opportunities from your project point of view?
So in our project, we use the process from fipronil to do the biorefinery of the woody biomass, and we specifically have a process that relies on non-food, renewable, and locally available lignocellulosic feedstock rather than agricultural crops. The primary feedstock is woody biomass, sourced from sustainably managed forest in Estonia and surrounding regions. This ensures a stable and traceable supply while avoiding competition with food or feed markets. We also maintain flexibility in the process to handle a variety of lignocellulosic residues, including plywood industry and forest residues. In parallel, at fipronil, they work closely with local forest owners and industry partners to ensure that all biomass originates from certified sustainable forestry operations. And by doing so, we can guarantee both long-term availability and environmental responsibility of our feedstock.
Thank you so much. So we can move now to the next question on industry demand and application sectors. So bio-based polymers are being explored in diverse applications from packaging to textiles and even clean mobility. Based on your project experience, which sectors are showing the strongest interest in adopting these materials and what barriers still exist for wider uptake? Maybe we can start now by Katien, so we change the order.
Yeah, so in our project, we focus on two sectors. One is the automotive, where we want to develop polyamides to use in electrical components of electrical cars. And this will strengthen the European value chain and create added value for the electrical vehicle sector. And on the other hand, we focus on the energy market, and a clear shift is visible in the energy market. And nobody can escape from the dependence on fossil-based energy sources like gas and fuel. And to better serve customers and our planet, new sustainable forms of power are required. And a promising direction of research aims at the production of clean hydrogen, which is expected to meet 22% of the global final energy demand. And that's why we work on the development of the anion exchange membranes for the fuel cells and electrolyzers. And if we look then, what are barriers for wider uptake? Well, there is the performance and qualification hurdles, because many bio-based materials still need to demonstrate equivalent or superior mechanical, thermal, and dielectric performance compared to fossil-based analogs, especially in high-demand applications. And often qualification and certification processes in industries are long and conservative. Another thing is scale up and production cost. Pilot scale synthesis of advanced monomers and polymers or from 2G biomass remains costly as long as the economy of scale is not high enough. And you also have to make sure that while scaling, you maintain consistency and purity. Another thing is market perception and risk aversion, because end users often perceive bio-based materials as experimental or lower performance options. So industrial actors tend to favor incremental innovation with proven reliability and well understood life cycle data. And also in our value chain, we have to do processing of the polymer materials. Also there, you can have barriers in processing compatibility because many bio-based polymers require adaptations of the current processing technologies like injection molding or extrusion, or new additives to ensure compatibility with established manufacturing lines, what increases the transition costs for the end users. That's it.
Thank you, Kathleen. So, Luis, what kind of industrial engagement do you see and barriers from polymers 5B?
So in this case, we are not with the strategy of cascade integrated process of extraction of bio-based monomers. So we are going to have the possibility to generate a huge amount of other chemicals compounds and bioactive compounds that can be huge demands in the cosmetic, pharmaceutical, food, and other fine chemistry industry. So these are a different goal of the call of the CBU, but in this case, with the progress of the extraction of bio-based monomers, move to this possibility, and in the concept of biorefinery, we can generate these compounds and get the opportunity to have more profit with them. So anyway, the goal of the biorefinery is also to have zero waste and zero pollution. For this reason, we are looking in this moment to explore all the possibility to generate these products and make the possibility to commercialize in different application industrial sectors in Europe. So the bio-based polymers that we would like to test is polyesters, polyamides, polyphenol compounds that we eventually have polyfuran if we have possibility to get the commercial one, not extracted from tomato, olive oil, or from wood in this moment. But all of this goal is to trying to mimic the fossil-based polymers like polyurethane, PET, and others, with huge demands in the textile sector, in the automotive, in particular, some compounds in the interior of the plastic that we would like to test and validate by one of our partners, the Iberolef in Portugal. So we have also the furniture, the coating for materials of furniture, and the polymeric resins that is interested by the Kiwi, that Vision, that is a company in the Netherlands that supply us with the biocatalysts that we are using to synthesize building blocks and the polymers, polyesters in particular. And the possibility of to satisfy the demands of the plastic in Europe is huge. If we get a possibility to have the right mechanical, thermal possibility to satisfy all these polymers, and in comparison with the traditional polymerization methods, so we are using very low temperature in comparison, of course, and some of the polymers are synthesized in water or aqueous media or solvent-free. So in this case, we're trying to reduce the CO2 emissions by this low temperature of the polymerization, and eventually get the polymers that satisfy the demands and the properties of industrial plastic. So the possibility of the polymer 5B to contribute to the bioeconomy and circular plastic economy in Europe is huge.
Thank you so much, Luis. So, Assunta, what's the polymers perspective?
Yes, thank you, Arantxa. Well, I have to say that we see strong interest coming from two main directions. One is the market scale, and the other one is the environmental urgency. From the market side, I would say that the strongest commercial pull is from packaging and automotive textile. This is because they are very large, established industries that are under clear pressure to reduce reliance on fossil-based plastics. And because they operate at scale, when they look for alternatives, the demand is real, it is immediate. In our case, this is backed by our partners. We have in the consortium BIOPYRANIA, which is acting as a first adopter for packaging applications. And then we have two players, that is Next Technology Tessile from Italy, which has a strong profile in textile application, and also Borstina, which is a company, and it is a supplier to major car brands, which gives us like a direct pathway into automotive interiors. So the interest, I have to say, is not just theoretical, it's already connected to industrial implementation. And at the same time, we also really consider like environmental urgency, especially in the case of agriculture. There we have, as mentioned, plastic mulch films that are accumulating in soil. So while the market can be smaller, the need for innovation is really urgent. However, regarding the barriers, I agree with Luis and Catherine. These barriers still slow down wider uptake, and I would stress two of them, which have been already mentioned. The first one is cost, because bio-based polymers are still more expensive than fossil-based ones. So scale up, process optimization are essential to be developed. And the second is the performance, but also the perception, because we need to demonstrate in a consistent way that bio-based materials can meet the same mechanical durability standards, so sustainability is not seen anymore as a compromise, no? So this is our perspective.
Thank you so much, Assunta. We can move now to the next question, but I would ask you to keep it a bit short because we are a bit behind schedule, and we need to have a bit of time for the questions from the audience. So maybe we can start now by Luis, if you want. The third question is about policy and regulatory frameworks. So EU policies such as the EU bioeconomy strategy are shaping the market for bio-based products. From your perspective, what kind of policy support is more crucial to accelerate the scale-up and adoption of bio-based polymers? I don't see Luis right now, so Sunta, if you want, you can start.
Yeah, sure. Well, from our perspective, the most important policy support needs to address cost and infrastructure, because bio-based materials, as just mentioned, still face the cost gap compared to fossil plastics. So policies could help by providing stronger incentives, for example, for bio-based production and research and development. This would accelerate adoption. And next we have to mention the end of life infrastructure, because even when bio-based materials perform well, the recycling or recovering system are not always ready to handle them. So we need policy support to co-finance and scale industrial recycling, recovery streams that are compatible with certified bio-based polymer, for example. Also, there is the need of support for pilot and demonstration scale facilities. This is also crucial. And also we need a European-wide harmonized standards for biodegradability, for example, and recyclability claim, because clear rules on end-of-life pathways are essential for credibility, for industrial planning, for consumer trust.
Okay, thank you. So, Katrien, what's your opinion on policies and regulatory framework?
Yeah, we see the following issues. One is there is a limited market incentives and green procurement uptake. So although the policy ambition is high, economic instruments like tax benefits or green public procurement criteria, carbon pricing reflecting the true cost of fossil materials are not yet strong enough to make bio-based polymers consistently competitive. And many public procurement policies still prioritize lower price over sustainability. And another issue we see from policy and regulatory framework is slow regulatory adoption to innovation speed, because novel materials and especially novel monomers have to pass REACH registration, and obtaining regulatory approval can take years, what can delay industrial application. That's it.
Thank you so much. I think Luis is back with us now, but I don't know if he's having any issues. So, Luis, are you here?
Yes,
Oh,
yes.
all right. Thank you.
I'm sorry.
So, how do you see regulation and policy affecting innovation in our field?
What I can say. So for me, in my opinion, of course, it is fundamental that the policy and the regulatory framework of the European Commission support this kind of the project. Otherwise, we don't have possibility to convince the industrial companies to support the extraction and look for a new bio-based monomers for the plastic materials. So the policy of European policy is fundamental, in my opinion, to get the possibility to prove concept that is possible to starting with new feedstock to get intermediary compounds and produce the bio-based polymers. So in this case, the CBU project supported by CBU and the European Commission, for me is fundamental, because otherwise we can look for the United States, China, and other countries, and they don't have the same strong support of this kind of strategy, bioeconomy strategy. And if we don't have the European Commission with these policies, so probably we don't achieve the Green Deal and the protection of the new generation of the huge environment problem that already start in the world and probably are going to worse in the future. So the plastic, substituting the plastic and to find new biodegradable polymers and biodegradable plastic and application from renewable feedstock is fundamental, and the European policy are supporting this. Congratulations to European.
Thank you, Luis, for your positive answer. So finally, let's talk about collaboration, which is why the BIOPOLY cluster was created. So it was created mainly to foster collaboration between projects, but beyond knowledge exchange, where do you see the most promising opportunities for joint action, whether in research, scale-up, or outreach to industry and policymakers? Maybe we can start by Luis now from POLYMERS-5B.
The same related with the previous question is the same. Fortunately, CBE call demand that we have already industries in the consortium to test and validate the materials. So this collaboration or cross collaboration is already associated with each of the projects in these clusters. So if we can demonstrate that these companies achieve the demand of the properties of the polymers and plastic that are the market for the huge market. So in this case, we can alert other industry that probably this is one way to trying to substitute fossil-based polymers and plastic materials, and they eventually have a better biodegradable condition, better environment, lower gas emissions, lower consumption of energy, and so on, that eventually protect the world and the new generations. So the opportunity of the biopilot cluster associated with the CBE. So let's go to demonstrate our success in this kind of application, textile, automotive, furniture, energy, and so on. And then eventually we are going to have opened the window or opportunity to the other plastic companies come into the Earth cluster, biopilot cluster, and eventually have a contribution to this field.
Thank you, Luis. So, Katrin, what do you think? What type of collaboration can have the greatest impact?
Well, I think, for example, joint testing and scale-up infrastructure, because yeah, we all need to do at some point piloting. If we have shared access to pilot facilities, that would be a help to transition from the lab to industrial scale. And maybe also something about standardization and benchmarking of testing protocols. That, for example, protocols for different property measurements, recycling, life cycle impact can be standardized and benchmarked across the different polymer families from the BIOPOLY cluster.
Thank you, Katrin. And Asunta, what's your opinion from Polymer?
Well, I see really a strong opportunity to develop like shared, for example, life cycle assessment methodologies or biodegradation testing, certification roadmaps, for example, because if we present consistent and credible sustainability data, we will build confidence, no, among industries and among regulators. So this is a very good opportunity, in my opinion. And also, we think that by coordinating outreach to the different industrial sectors we are targeting, in some cases they are the same sectors indeed, and the same as well as to policymakers, for example, we can deliver a clearer and stronger message about the economic and environmental value of the, let's say, residue-based biopolymers.
Thank you so much, Asunta, and thank you all for providing your perspective from the different projects work. So now let's move on to the Q&A. We have two questions from the audience, so we can address quickly them because we have 3 minutes left. So the first one is BSG is highly susceptible to microbial spoilage and in particular wet BSG. How are you addressing the logistics problem? I think, Asunta, this is for you.
Yes, I think it's mine. So BSG has a very short lifetime indeed, because it is very rich in humidity. So it comes with like 90% of moisture from the brewing process. But eventual, and this is also the advantage of using it as like a feedstock to be valorized in this context, because the microbial spoilage do not affect the properties and characteristics of the lignocellulosic biomass, the lignocellulosic part, the fiber part of the PSG we are going to develop further, because we separate proteins according to the food first principle. So that one is just taken out of it, and next we work on the fiber part. So that is not affected indeed. So this is the first point. The second is about, I forgot the second point.
How are you addressing the logistics problem, it says?
The logistic problem is a problem indeed. The point is that during the process, during the project, the logistics is just transportation according to sustainability practice, because we have in our project like a green procurement activity in ACT. So according to that specific categories, that is the transportation, we can address transportation. The best way to go once ideally these processes are implemented in the real case is that the biorefinery could stay in a way close to the brewery centers, for example. This is one way we could address this.
Thank you so much. So the other question that we have is for Katrien. It says, do you think the amino acids produced through fermentation process can have application as functional ingredients in food application? I think Katrien just left and came back. So, Katrien, are you here with us? No, I think she's having issues. So we can address, we have a last question in general for the 3 projects. It says, are you open to collaborating beyond current project partners? If suitable, we would be interested in testing the biopolymers produced within the project on our spin boy melt spinning line for filament yarn production at Polytex.
I think talking about spinning should be a question addressed to POLYMEER project, I guess. So what we can do is that we have in the project like the possibility to collaborate externally to the consortium, provided that all the partners agree with that. We also created like a how to say, like an industrial advisory board for companies, for example, where we enable the companies to participate to some of our meetings to follow the results of the project. So yes, we may be open to this.
Thank you, Asunta, for your answer. So we don't have much time left. If anyone wants to ask another question, feel free to reach us on our different communication channels, either through the website or our social media. And we've reached the end of our session now. A big thank to all the speakers, Asunta, Luis, and Katien, and also Simone Macaferri, even though he was not able to connect online, but he was supporting us in this webinar. So this webinar starts the starting of this exciting collaboration between the three projects, POLYMEER, BIOPYRANIA, and POLYMERS-5B, built on shared goals, innovation, and sustainability. So we look forward to continuing this journey together and welcoming new opportunities in the future. Thank you once again for being with us and have a great day. Just notice that the recording of the session will be uploaded to our YouTube channel and will be shared through the website and social media channels. Thank you all.
Thank you.
Thank you very much, Arantxa.